Hi everyone! In this video, we'll see an application of the Martingale Stopping Theorem to finding hitting times of random walks. For motivation, let's consider this random walk. So we're going to start at z0 equal to 0, so right here, and then with probability 1/2, we'll add 1, and with probability 1/2, we'll subtract 1. So that is, we'll start here, and we'll just kind of bounce around for a little while. Maybe something like that. And we're going to stop at the time capital T, which is defined to be the first time that z sub t, our random walk, is equal to either minus a or positive b, for some values a and b. So suppose that minus a were minus 4 and b were 3, we would walk around until we hit one of those two values and then stop. So this is a very natural random walk to study, and there's some natural questions that we can ask about it. For example, we could ask the question, what is the probability that z sub capital T is equal to b? That is, I know I'm going to stop at either minus a or b. What's the probability that I hit b first before I hit minus a? We can also ask, what is the expected value of t? That is, how long an expectation is it going to take for me to stop, for me to hit one of these two end values? If you haven't seen this before, the answer to these should not be at all obvious, but it turns out that we can answer them fairly cleanly using the Martingale Stopping Theorem. Let's start with this first question. What is the probability that z sub t is equal to b? The first thing we can note is that the Martingale Stopping Theorem applies to the z sub t's. In particular, item 1 is satisfied since zi is less than or equal to the maximum of a and b for all I less than or equal to t. So as in the previous video, technically we should replace zt with some z twiddle t, where z twiddle t is something that stops at time t. Okay, so given that, we can apply the Martingale Stopping Theorem, and we can conclude that the expected value of z sub t is equal to the expected value of z0, which is equal to 0. Thus, we have 0 is equal to the expectation of z sub t. But what is this? This expectation is just the probability that z sub t is equal to b times b plus the probability that z sub t is equal to minus a times minus a. That's because there are only two possible values for z sub t. There's either b or minus a, and here we're just writing out the definition of the expectation. But now we can observe that this thing, the probability that z sub t equals minus a, is just 1 minus this thing, the probability that z sub t equals b, because these are the only two things that could possibly happen. And so simplifying, this becomes 0 equals the probability that z sub t is equal to b times b plus a minus a. But at this point, we could just solve for this. We could just solve for the probability that z sub capital T is equal to b. So this implies that the probability that z sub capital T is equal to b is equal to a divided by b plus a. So that answers this question. And all we had to do was apply the Martingale Stopping Theorem and do a little bit of algebra. And now we know that the probability that this random walk stops at b before it stops at minus a is proportional to a, basically. And similarly, the probability that it stops at minus a rather than b is proportional to b. Cool, so we've answered this question. Let's move on to the next question. What is the expected value of t? How long do we expect to walk around before we hit either minus a or plus b? To answer this question, let's define a new martingale. So we're going to define y sub t equal to z sub t squared minus t. Why are we doing this? Well, it's a little bit magical. We'll see in a moment why this is the right thing to look at. First, I claim that these y sub t's that I've just defined like this are a martingale with respect to z sub t. So let's verify that. So we need to show that the expectation of y sub t, conditioned on z naught up to z t minus 1 is equal to y sub t minus 1. So to show that, let's actually compute this. So this is equal to 1/2 times z sub t minus 1 plus 1 squared plus 1/2 z sub t minus 1 minus 1 squared minus t. And here we're just using the definition of the expectation along with the definition of y sub t. That is, with probability 1/2, z sub t is going to be z sub t minus 1 plus 1. With probability 1/2, it'll be z sub t minus 1 minus 1. And then we're just plugging that into the definition of y. Simplifying this expression, we see that this is equal to z sub t minus 1 squared minus t minus 1. And fortunately, that is exactly the definition of y sub t minus 1. So indeed, this is a martingale. Check. Okay, so we've just shown that these y sub t's are a martingale. We don't know yet why we defined them, but the next thing I claim is that the Martingale Stopping Theorem applies to these yt's. To see this, we're going to go for thing 3 in the statement of the Martingale Stopping Theorem. The main thing that we have to show is that the expected value of t is finite. So claim the expected value of t is finite. To see this, observe that for any value of z sub t, the probability that we stop after a plus b additional steps is at least 1/2 to the a plus b. Basically, if we haven't stopped yet, then we're somewhere in this interval between minus a and b, and there's some probability that I just walk in a straight line up, 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 until I hit b here. And what is that probability? Well, it's 1/2 to the number of steps I take. How many steps do I take? Well, it's at most a plus b. So therefore, the probability that I stop after a plus b additional steps is at least 1/2 to the a plus b. That implies that the expected value of t is at most 2 to the a plus b times a plus b. And here we're just using the fact that the expected value of a geometric random variable with expectation this is 1/that. Okay, so this is a pretty loose bound. We're hoping to answer this question much more precisely, but this bound is enough to show that e of t is actually finite. So now we know that this is true, and we should verify this. So the expected value of y sub I plus 1 minus y sub I, conditioned on z naught up to zi. Well, this is at most 1 plus 2 times the absolute value of zi, using the definition of yt here. And this in turn is at most 1 plus 2 times the maximum of a and b. Because if we haven't hit the stopping time yet, z sub I is always going to be at most a or b. And once again, technically, we should replace z sub I with some z sub I twiddle or something like that. Okay, so thing 3 is satisfied by these yt's with stopping time capital T. Great. Finally, we can use this to actually answer our question and compute the expected value of capital T. To do this, let's first recall that we showed earlier that the probability that z sub capital T is equal to b is a divided by a plus b. Okay, now let's compute the expected value of t. We just showed that the Martingale Stopping Theorem applies to the y sub t's, so therefore 0, which is equal to e of y0, is also equal to the expected value of y sub capital T. And by the definition of the y's, this is the expectation of z sub capital T squared minus the expected value of capital T. So solving for the expected value of capital T, we see that the expected value of capital T is equal to the expected value of z sub t squared. But we know what this is. This is just b divided by a plus b times a squared, because remember, this is the probability that z sub t is equal to minus a, using the thing we already showed, plus a divided by a plus b times b squared. And if we simplify this out, this becomes a times b. So this answers our question. What is the expected value of t? The expected value of t is equal to a times b. Cool. Okay, so what you should take away from this example is, well, first that we have these sort of very nice clean answers for these questions, that the probability that z sub t is equal to b is a divided by a plus b, and the expected value of t is a times b. But the more important part is that with the right application of the Martingale Stopping Theorem, we can quite cleanly answer these questions. It involved a fair amount of cleverness to come up with this new martingale, but once we had it, the actual computation is not very difficult. So this illustrates the power of the Martingale Stopping Theorem. Let's see another example of how we can use the Martingale Stopping Theorem to analyze hitting times. So let's consider what happens if the random walk that we're interested in looks the same, except now 1/2 is replaced with p and 1 minus p. So that is, if p is not equal to 1/2, then either there's some bias that I'm going to keep going this way, or there's some bias that I'm going to keep going that way. And we can ask the same questions. That is, let capital T be the first time that z sub t reaches either minus a or plus b for some values a and b. And we want to know, what is the probability that z sub t equals minus a? That is, what is the probability that this random walk hits minus a before it hits b? And we also want to know, what is the expected value of capital T? How long do I expect to spend walking around before I hit either minus a or plus b? So here are the answers to these questions. For p not equal to 1/2, what is the probability that z sub t is equal to minus a? Well, it's this thing, 1 minus c to the b divided by c to the minus a minus c to the b, where c is 1 over p minus 1. And what is the expected value of t? Well, it's this thing, which I'm not even going to try to read out. What's important here is not the exact form of these answers, which look pretty ugly, but rather that we can pin down these answers exactly, and we're going to be doing it using the Martingale Stopping Theorem. So the actual statement of this result isn't so important, at least for us. The thing that's important is that we can prove it reasonably cleanly using the Martingale Stopping Theorem. Sorry, I just realized that there's a typo in this theorem. I had a z sub little t here, and these should be z sub big t's. Sorry about that. Hopefully that's clearer now. Let's start by answering the first question. We want to show that the probability that z sub capital T is equal to minus a is equal to this thing. Our first obstacle is that z sub t here is not actually a martingale because it's biased. So instead, we're going to define y sub t that is a martingale. So what we're going to choose is we're going to choose y sub t equal to c to the zt for some appropriate constant c. And here we're going to want to pick c so that this thing is a martingale. To see how we should pick c, let's compute the expectation of yt conditional on z naught up to z t minus 1, and see how we should pick t in order for this to be equal to y sub t minus 1. So by definition, this is equal to p times c to the z sub t minus 1 plus 1 plus 1 minus p times c to the z sub t minus 1 minus 1. Simplifying, this is equal to c to the z sub t minus 1 times cp plus 1 minus p divided by c. We would like to choose c so that this is equal to 1. Because if we can do that, then this thing, which is left over, is just y sub t minus 1, and we'll have shown that the y sub t's form a martingale. So if you work it out, the solutions to this thing being equal to 1 are c equals 1 and c equals 1 over p minus 1. C equals 1 is not going to give us a very interesting martingale, so we're going to choose c to be 1 over p minus 1. So let's write that up here. C is equal to 1 over p minus 1. And note that that is conveniently also what I defined c to be up here earlier. Okay, so now we know that these y sub t's with this choice of c form a martingale. You might be wondering, how the heck did we come up with this particular form of y sub t? It's not at all obvious, and it's okay if this appears a little bit magical. A theme that we're going to see in this lecture is that coming up with the right way to apply the Martingale Stopping Theorem can be pretty tricky, and you basically just have to do a bunch of examples to get a knack for it. Okay, but now that we have these y sub t's, let's apply the Martingale Stopping Theorem to it. I'll let you figure out why the Martingale Stopping Theorem applies. Given that it applies, we have that 1 is equal to the expectation of y naught, which by the Martingale Stopping Theorem is equal to the expectation of y sub capital T. Well, by the definition of the expectation, and also of the y's, this is the probability that z sub capital T is equal to minus a times c to the minus a, plus the probability that z sub capital T is equal to b times c to the b. And simplifying this, in particular using the fact that this is equal to 1 minus that, this is equal to the probability that z sub t is equal to minus a times c to the minus a minus c to the b plus c to the b. And now we can solve for the probability that z sub t is equal to minus a, and we get that the probability that z sub t is equal to minus a is 1 minus c to the b divided by c to the minus a minus c to the b, which is exactly what we claimed up here. So, check. Cool. So this answers this first question, where again I accidentally had that typo there. The probability that we hit minus a before we hit b is equal to this funny expression. Okay. But again, the most important thing is not actually what this expression is, but that we could actually derive it quite cleanly if we just sort of guessed the right martingale to look at. Let's move on to the next question. We want to show that the expected value of t, the expected time until this walk hits either minus a or plus b, has this form, where again c is equal to 1 over p minus 1. To do this, we're going to define yet another martingale. So we're going to define q sub t equal to z sub t minus alpha t for some alpha which we're going to choose in order to make this a martingale. So let's see how we should choose alpha. So we have the expectation of q sub t conditioned on z naught up to z t minus 1. So we're going to write out what this is in terms of p and alpha and so on, and then we'll see how we need to pick alpha in order for it to be equal to q sub t minus 1. So by definition of the expectation and also of the q's, this is equal to p times z sub t minus 1 plus 1 plus 1 minus p times z sub t minus 1 minus alpha t. And simplifying, this is equal to z sub t minus 1 plus 2p minus 1 minus alpha t. And what we want is for this stuff to be equal to minus alpha times t minus 1. Because if this stuff is equal to that, then this whole thing is equal to z sub t minus alpha times t minus 1, also known as q sub t minus 1. And so if this were true, the q sub t's will form a martingale with respect to the z sub t's. So let's set these two things equal and solve for alpha. We have 2p minus 1 minus alpha t is equal to minus alpha t minus 1. And solving, we get that 2p minus 1 is equal to alpha. So let's set alpha up here equal to 2p minus 1. Okay, so now we have our qt's. They're defined like this for some reason. And now we're going to apply the Martingale Stopping Theorem to the qt's. Once again, I'll leave it to you to see why the Martingale Stopping Theorem applies. But when we apply it, we get that 0 is equal to the expected value of q naught, which is equal, by the Martingale Stopping Theorem, to the expected value of q sub capital T. And now, using the definition of the expectation, this is the probability that z sub capital T is equal to minus a times the value of q sub t if z sub t is equal to minus a, which is minus a minus alpha times the expected value of t, plus the probability that z sub t is equal to b times b minus alpha times the expected value of t. But fortunately, we already computed this, and this is just 1 minus the other thing. So we already saw that this was equal to 1 minus c to the b divided by c to the minus a minus c to the b. And we already saw that this was equal to 1 minus that. So now we have this equation. So this is just some linear equation with the expected value of t in it. So we can solve for the expected value of t. And if you try to do it, what you get is this, I promise. So that answers this question. Hooray! Once again, this particular result isn't so important, at least for this lecture. But the thing that's important is the fact that we can find it exactly. We can exactly figure out the expected value of t just by cleverly defining a martingale and applying the Martingale Stopping Theorem. I think this is really cool. This is just like so slick. I hope you think it's cool too. That said, even though I just said that this form isn't particularly so important, you might be wondering, what the heck does this look like? Here's some graphs for some quick intuition. So here's what it looks like for a equal to b. So this graph is a equals b equals 20, and this graph is a equals b equals 100. So as p approaches a half, we already saw in the first part of the video that the expected value of t is going to be a times b, which in this setting, when a is equal to b, is a squared. So here, when p is equal to a half, here and here, the expected value of t, that's what's on the y-axis, is going to be a squared. So here, if a was 20, this is 400, and here, if a is 100, this is 10,000. So that checks out. And now we're asking, what happens when we deviate from a half? And what this is showing is that if I deviate from a half by just a little bit, like if I go to 0.6 or something, then all of a sudden the expected value of t drops a lot. Essentially, this is saying that as soon as there's any bias away from a half, then I expect to hit the ends of this interval minus a plus a much, much, much more quickly. Which should kind of make sense. As soon as there's any bias, I'm much more likely to off in that direction and hit plus a or minus a, respectively. Okay, so to recap, what we saw today is that the Martingale Stopping Theorem is a powerful tool for analyzing the hitting times of random walks. However, it's not at all obvious how to set it up. We came up with some pretty unintuitive martingales that just happened to work out. These might seem a little bit magical at the moment, but if you see a bunch of examples like these, you might start to develop some intuition about how to do it. Okay, so that's all for this video. Thanks for watching.